Alright, welcome back guys, and today we're going to be going over 1.4 part 2, and last time we left off we learned how to find the equation, finding the equation of an inverse. So today we're going to be learning about how to graph a function in its inverse, how the domain and range get affected, and we're going to learn how to um, do function composition to check if they are inverses. So example 6. What are the graphs of f of x and its inverse f of to the power of -1, which is like the f of inverse of x, plus or minus square root of x. So first things first, let's graph this x squared, which should look like so. I'm gonna use this. So far, like in our classes, we've been using mustard yellow for like the original, and we've been using like this bluish color for the inverse. That's not the same blue, but you understand what I mean. So I'm gonna use this mustard again for x squared, which looks like so. So this is like this is my general like x squared graph. And the inverse, if we review over the principles that we learned about before, we know that this graph is going to reflect off this line right here. The y equals x line, are like the origin. So what I could really do, let's say for example, Mr. Hong, or you said like, oh, I don't know how to graph this. I don't even know what the inverse is. Sure, you can just use the principles that we talked about in the first day and just reflect this off the y equals x axis. Or you can just switch your x to your y, because remember, in class, all day in class, last class was, I told you that x is to y and your y's turn into x's if we see the word inverse. So it would become 1, 1, then let's do the left side first. 1, 1, then 2, -2, 5, so it'd be 5, 2. No, it's 4, sorry. 4, 2. And it should be like this. 4, 2. Or -1. Okay. And it looks like this. So my graph now looks like so. My graph is not perfect. Oh, you're fine. So this part is done. As in, I graphed both my plus or minus square root of x and x squared. So the second part says, what restrictions on the domain of the original can we do so that we can make the inverse of f of x a function? Because we can see that the function right here, this blue line, or my inverse, is not a function, because if I do the vertical line test like so, I know that I fail my vertical line test here twice, and if I go to the left twice and twice and twice. So really, I need to cut this graph in half, as in I need to cut it symmetrically using the x axis, or y equals 0, as my crease. So I can really just cut this out, but I'm talking about my after. Didn't they say what kind of domain restriction can I have on the original? So on the original, shouldn't I just be able to cut like my y-axis, or my axis of symmetry, or my x equals 0? So I can just say that my domain can be starting at 0 and including it, because I can have this 0 still, right? I can still have this point in my graph. And let's say, for example, I want to cut the negative part. I want to keep the positive part. So the way that we can write positive, or I want to keep all the positives, is with the infinity sign and a quotation, or not a quotation, a parentheses. This makes a lot of sense because I want to, what restrictions of the domain of the original makes sense. As in, I want to cut this in half, right? I want to cut this orange graph in half because it's my original, to make my blue into a function, or my inverse, or my after. So I need to restrict the domain, right? I need to cut this in half by restricting the domain, and I do that by including 0 and only keeping 1/2. And I just decided that I wanted to keep the right half, or the positive half. So I wrote this restriction. So if I drew this, my after would really look like, where's my white? So this part would just go away right here. Looks like I gotta make it 7.5. Yeah, so I can just, this graph would eventually go away like this. And then what would happen to my graph here is that this would go away. My negative half of my square root of x would go away too if I limit the domain, because now I'm talking about 0 to infinity, as in my graph became 0 to infinity, and same thing with my original. 0 to infinity became my new range, because we know that when we take the inverse, this becomes range for the inverse. Nice. Thought I did a pretty good job there. Finding the inverse when the domain and range have restrictions. So let's read the example. Let's say, for example, I don't know how to do this problem. Let's read the example. Example 7. Let g of x equal square root of 2x minus 4. What are the domain and range of these graphs? And let's say, Mr. Hong, I have no idea how I can figure out this graph. Or I don't know what that graph even looks like. Sure, but there's no excuse of not doing this problem, because you have Desmos and you have your graphing calculator. I will use Desmos for learning purposes. So I have this graph, right? And really, nowhere does it tell me to draw it. It tells me what the domain and range of g of x is. So using Desmos, I can go all the way down to 0 and 2. 2 is going to be my most left, and it seems like it's going to go on forever. So my domain is going to be 2 to infinity, and my range, where is it? There it is. My range, my lowest point is 0, and because you know that this graph right here, it has like an arrowhead right here but going diagonal. So I know eventually like it'll go to infinity. So I will write 0 to infinity for my range. So now it asks me for the inverse of g of x. We learned last class how to find the inverse of an equation. And to review, that is 1, switch x and y, and 2, solve for y. So let's try it out. G of x, I'm going to write y. Y is equal to square root of 2x minus 4. I want to use like this reddish color right here for my y. And the opposite side of the spectrum, I'll use this x. Okay, so step number 1. Step number 1, I gotta switch my X and my Y. And that also means like everything else that's written in black, I cannot move. As in, literally, if it doesn't say Y, I cannot switch it. Like so. Now I gotta solve for Y. How do I do that? I gotta first get rid of the square root. And I know that square root is the opposite. I know that square root is the opposite of squaring. So what I gotta do is I got to square this, like so. So x squared is equal to 2y minus 4. And then now I just gotta add 4, which is x squared plus 4 is equal to 2y, then divided by 2. I'm gonna write it right over here because it's my final answer. So y is equal to x squared divided by 2 plus 2. And I got this plus 2 because I just simplified 4 divided by 2. But I don't have like I don't have a coefficient to divide this 2 with, so I just kept it. I could also write it as 1/2 x squared, but it's your preference. Nice. Let's keep moving on. What are the domain and range of your inverse? So there's a rule. Your domain becomes your range, and your range becomes your domain. So for like speed wise, you can just say like, oh, all I really gotta do is switch these, and I will switch them. Oh, since this is my range, which I will write in mustard. I'll write both of these, and I'll write my domain in mustard, and I'll write my range in this blue color. Wrong blue. This blue. So you see how my domains becomes my range, right? And my range, my old range, becomes my domain of my inverse. Aren't they? They are asking me for my inverse, so they're asking me for these. So my new range, or let's start with domain because I like starting with my x values first. My domain becomes 0, infinity because of this right here. It just switches, but it still keeps its values. That means that my new range has to be like the exact same thing, but just opposite, or like different. So this is gonna be literally to infinity because it is the rule of our domains and range switches. But that doesn't seem right. So let's check it. So let's do 1/2 x squared plus 2 plus 2. There we go. So the domain doesn't seem like it's all real, or it's limited. It just seems like it's all real numbers, and this is why this is the problem, because wasn't our original graph square root of 2x minus 4? Wasn't our regular graph just half of this, really? And that's true because we have to let this be a function. So we always use the positive side. But whenever it reflects off the y equals x axis, or y equals x line, whenever I reflect it, we have to put both of them now so that it can, because it can still be a function with having both sides. So really this domain is not right? Because we saw that in our graph. Our domain is actually gonna be all real numbers. which is like this. Let's check our domain, or let's check our range. Our range is square root of 2 to infinity. So our lowest point is right here. 2 to infinity. So this is correct. Nice. Is the inverse of g of x a function? Why or why not? What do you think? Is this graph, this red graph, a function? I think it is. Because it doesn't have any repeating x values, and it's okay with the vertical line test. It only passes one time. So this is a yes. It passes the vertical line test. Why did I put 2 L's? The vertical line test. Nice. All right. Composing inverses functions. So this is the meat of the question, and we always have to think of, okay, we're thinking of inverse, so eventually like my x is going to be my y and my y is going to be my x. And you know, that eventually that's going to be true, but let's read the question. Example 8. Use composition of functions to determine whether these functions, blah blah blah, f of x and g of x are inverse. I forgot to type out are they inverse? But for saving space, we're not going to write it. And I want to draw lines to kind of just separate this, because we're going to have to do 2 steps. In our notes, in our first page, we saw that f and g are inverse of each other if and only if f of g of x is equal to g of f of x, which is equal to x, or if it's written the different way, which is f of g of x is equal to g of f of x, which is equal to x. So really, we need to have x's for both of them. So that's why we have to do 2 parts or 2 halves of it. I have to do f of g of x, and I have to do g of f of x. And it doesn't matter how you write it, right? There's 2 ways to write this. F of g of x. F of g of x is the same as f of g of x. It's the same thing. Okay. And whenever you see this problem, or if you write it down yourself, you will always draw these arrow keys telling you your steps. You start from the back and you go towards the front. Because you have to evaluate g of x first before you can evaluate f of g of x. And I want to start with a story. So when we talk about this picture right here, so when I talk about these, we know that this, if you haven't seen these before, what you do is you get the smallest one and then you keep putting them into the bigger one, and it keeps going on into levels and levels, as in you can like eventually just leave with just this doll. But let's not think about the small ones. Let's just talk about the last 2. If we're talking about f of g of x, if we're talking about f of g of x, we have to assume that g of x is this, and f of x is this. But whenever I want to put the whenever I want to have like the end of my product, right? Like with every single like dollars inside my biggest one. If I'm talking about my last step, what do I have to do? Don't I have to like open the big container so that my smaller item can go inside my container and then I have to close it? It's the exact same like steps. So whenever I try to do this problem, I have to first open my container, or I have to start like from the biggest. And that's gonna seem weird, but step one is actually going to be right outside equation. I forgot the E. As in, my outside equation is this F, and my outside equation is this G. I will be starting just on the left side for example purposes. So f of x is equal to 1 half x minus 3. And for note purposes, I'm going to write this in red. My x's are in red. Because you know eventually I will replace these. Step number 2. Replace x with back equation. And what that really means is that this is my back equation, right? I'll write this as purple. This g of x is my back equation. My f of x is my back equation. So what that becomes is that my x is right here is becoming, or I'm making my g of x an input for my equation. So it really becomes like this. I said red. G of x is equal to, and everything that's black, you see like how I'm like still keeping it the exact same place. 1 half g of x minus 3. So I still kept everything the same. I just replaced x with g of x, as in this x has to also become g of x. And I knew that it's g of x because it's my back equation, or like my equation that I have to put in eventually. Okay. So let's say that you do understand that step. Good. I hope so. Because step 3 is replace g of x. That's not a universal step. Replace equation with function. And I think I wrote that too small. I'm not gonna cheap out on you guys. Okay. So let's say, for example, this is true, or I want to do this step. How do I apply that step? And it's gonna look something like this. I don't have to do it on the left side because eventually this will be my like final answer, f of g of x. But if I think about the word equals to, we have to also think about like let's say, for example, the star is $100, and let's say like my phone, right? My phone is $100 as well. That means that my star is equal to my phone, which is equal to $100, which is equal to a star, which is equal to a phone. I could just continuously write this equation if I wanted to, which is the phone is equal to a phone because they're the same thing, but star has the same monetary value. The monetary value is $100, and I could just keep going on and on and on about like these three things being equal to each other. I can still do the same thing with just 2 as well, as in $100 is equal to star, and that's equal to $100, and that's still equal to a star. It doesn't change the value of it. We're just saying that these two have the same monetary value. So if I want to talk about g of x, I said that g of x is equal to 2x plus 6. So couldn't I just switch my g of x for 2x plus 6 for free? And that's true, you can. So what I can do is f, which I will start using this area because I'm running out of space and I do not want to cheap out on you guys. F of g is 2x plus 6. 2x plus 6 is equal to, my black is still going to move, 1/2. Because all I'm doing is replacing this g of x. 2x plus 6 minus 3. I still haven't touched my like foundation, right? I haven't changed my half, as in my half is still here, and my minus 3 is still here. All I did was change my input. But now it seems like I'm ready, because what can I do with this 2x plus 6? Let's see. What I can do now is I can simplify. And this is the same thing as combine like terms or PEMDAS. Whichever way that you want to think of it. So I know that my multiplication goes before my subtracting and addition, so that I'm going to multiply this. And now I'm just going to write this all in black, because now my black is going to mesh with my red. So half of a 2x is an x, and half of 6 is a positive 3. And then this is just going to come back down. Okay, now I can do this, which cancels, right? So it's going to be x is equal to, and remember what I said, like, oh, like I can infinitely interchange these, like I can infinitely interchange these values, or like these things that represent really $100, or they all represent star. I can change this 2x plus 6 back to something else. I can change this back to g of x. And that's what I want you to do, because isn't the question is asking us what is f of g of x. So it's important for me to change this back to f of g of x. Nice. So I ended up with x, and that's perfectly fine. We simplified this as much as we could. So if I went back and labeled my steps, this would be step 1 right here. Then this would be step 2. This is step 3. And then this is step 4. Not too bad, right? But this is only half of the problem, because I can't tell if these are inverses of each other if I only do composition of only one side of it. I have to do composition of both sides. Stated in my rule, stated in my rule right here. I have to do both f of g of x, and I both have to do g of f of x. So let's do the first thing. Let's do the first step again. Right outside. So I am going to g of x is equal to 2x plus 6. And I'm going to go back and replace my x's with red to just show visually what it is. This is step 1. Step 2. Replace x with back equation. So my back equation for this is f. So I can do g of f of x is equal to my 2 transfers, right? My 2. But my x turns into my x turns into f of x. Plus 6. Nice. Step 3. Replace f of x, or replace equation, which is f of x in this situation, with function. What does my function of f of x equal to? It's listed right here. F of x is equal to 1/2 x minus 3. Okay. So I can write g of, and when we think about this problem right here on the left side of my equal sign, did I have to really switch out my equation to x plus 6? Because I changed it back. So really, I don't really need to change this side. So for space efficiency's sake, I will not. But I'll keep it as f of x is equal to 2. Remember, this 2 still transfers. And my f of x is going to turn into, which now I really have to write small. This is equal to 1/2 x minus 3. Then plus 6. Because this plus 6 hasn't been touched yet. Nice. So I did step 3. Step 4, simplify. So if I simplify this, yeah, I'll just write this for note's sake. G of f of x is equal to, and I know that in PEMDAS, multiplying comes before adding and subtracting. So I'm going to multiply or distribute. And this is going to be x minus 6 plus 6, because the 6 comes back. This 2 times negative 3 is negative 6. Then now I combine like terms by adding and subtracting, which really ends up being x is equal to g of f of x. So why is that important? Because I haven't done my step 5 yet. Step 5. Evaluate f of g of x is equal to g of f of x, which both of them have to equal x. If I come back to my example of my star is equal to phone is equal to $100, you see how I can infinitely interchange these over and over again? I need to do the same for f of g of x is equal to g of f of x is equal to x, which is equal to g of f of x, which is equal to f of x, or f of g of x. This and that have the same concept, as in I have to say this is equal to that and that and that and that. So in my in my problem, is that true? My g of f of x, or my f of g of x is equal to x. My g of f of x is equal to x. My f of g of x is equal to x, which is still equal to g of f of x. So this is true right here. So I can say, if yes, they are inverse. If no, they are not inverse. So with this conclusion, we can say it is inverse. And this is the final answer right here. This is the final answer. Because, let's come back to the question. The question is asking us to use function composition to determine whether a function is our inverse. So I have to say they are inverse because they all equal to x. This part right here is the important part. Both of them equal to x, and that's how we connect both of those equations together. All right, and let's do this problem right here. Example 9. Example 9, I'll be going a little bit faster, maybe. I'm not gonna write the steps for sure because I have the steps already here. I'm just gonna label my steps like as like 1, 2, 3, like so, like 1, 1, 2, 3, 4. But what I am gonna do is I'm gonna draw another line. So this is gonna be f of g of x, and this is gonna be g of f of x. Use composition of functions to determine whether the functions f of x and g of x are inverse. I forgot to write are inverse. But let's draw our arrows. So step 1. Write the outside equation. 3x minus 2 is equal to f of x. Whoops, I wrote this in opposite order. Step 2. Replace x with f of x. Or, yeah, replace x with the inside equation. So, f of g of x is equal to 3 1/3 x plus 2 minus 2. As in, my x changed. Where's my purple? I don't want to use purple. I want to use blue to show my transfers. My x became this parentheses, or like this equation, because I replaced it with g of x. This 3 came here, and minus 2 came here. So I haven't touched the 3 and I haven't touched the minus 2. Step 3. I already did step 3. Okay, let's just simplify. This is also 2 and 3. I should write that like this. 2 and 3. So step 4. Simplify. 3 gets multiplied into both of these. So it's going to equal to x plus 6 minus 2. So this comes out to be x plus 4 as my final answer. Is equal to f of g of x. So here, if I already know step 5, I know that it has to equal to x, but my final answer is equal to x plus 4. So I can already say that right here, if I know for sure that my math is perfectly correct, I can say like not inverse in the bottom. Because I already proved that it's not inverse because one of my equations are not equal to x by itself. Is x plus 4. So do I have to do this part right here? No, I don't have to. But for note purposes and for like making sure that I did everything correct, I will. And you will. G of f of x, g of x is equal to 1/3 x plus 2. And watch, you see here how I skipped a step? As in, I said that I want to do g of x, but I just put in the equation by itself. You can do that. You're allowed to do that. Step 2 in this part right here, this is like training wheels. Like if you need it, you can, but if you really don't, you can skip from 1 through 3 immediately. That's what I did here on accident. So if I want to do that, g of f of x. So my x becomes f of x is equal to what? Is equal to 1/3. And I told you this x can be just skipped into f of x, but I just want to write this for space purposes. So couldn't I just write this as 3x minus 2 and then plus 2? Because I know that f of x is equal to this equation, so I can just skip a step. And then, now, I just distribute. So 3 times, or 1/3 times 3 is x, or 1, and minus 2 divided by 3 is 2 over 3, plus 2. See, like this problem right here, like x minus 2 over 3 plus 2, I know for sure this is not equal to like x by itself, right? If I simplify this, so I'm gonna stop here because I know already that this is not a inverse that I already wrote. Because if I simplify this, this will be what? X minus 2 over 3 plus 6 over 3. So this becomes 4 over, so this becomes x plus 4 over 3 is equal to g of f of x. So g of f of x is not equal to f of g of x. And both of these do not equal to x. And this proves that these are not inverses of each other. So using function composition, I proved that both types of both equations of f 3x minus 2 and 1/3 x plus 2 are not inverse using function compositions. So that's it for 1-4, and that concludes the unit. So next class we'll review, and then the class after that we'll be taking our test. But for now, see you guys.